Welcome back, Focus Learners. Today, we're stepping into the field to embark on a massive, metaphorical dig. We are taking a hammer and chisel to the Cambridge AS and A-level computer science syllabus, specifically zeroing in on subject code 9618. Our target? One of the most absolutely critical, yet consistently mishandled structures in your entire syllabus, cues as abstract data types, or ADTs. I like to call our approach today the paleontologist strategy. Because, just like a paleontologist carefully digging through fossil layers to reconstruct a complete massive dinosaur skeleton, we are going to dig through the layers of complex past paper questions to reconstruct the absolute perfect maximum mark exam answer. It's a precise science. Now, to set the stage, let me introduce you to two archetypal students I see literally all the time when analyzing past papers, specifically across the board from the 9713 days right up to our current 9618 focus. First up, there's Alex. Now, Alex overloads his paper with raw, unfiltered computer science facts about cues. He's talking about first in, first out, he's listing out pointers, he's drawing arrays. But he provides absolutely zero analysis. It's just a data dump. Then, on the other end of the spectrum, we have Sam. Sam looks at the clock, panics, rushes through the paper, completely misses the specific command word requirements, scribbles down a super generic piece of pseudocode, and just moves on. In this explainer, we are going to look incredibly closely at their flawed approaches, the harsh red pen marks they typically receive, and most importantly, exactly how you can avoid their fate to lock in those top-tier grades.
Right, so why are we focusing so heavily on this? Well, the Cambridge Senior Examiner's report contains a pretty stark, unavoidable mandate. It literally says, Q as an abstract data type is one of the most misunderstood areas in computer science. That's a direct quote, guys. So our primary mission today is to fix that right now. Think back to Alex and Sam for a second. When Alex writes a massive half-page paragraph defining a Q but completely ignores the context of the question, let's say it was about a printer spooler or CPU process scheduling, the examiner gives him minimal marks. He didn't answer the prompt. When Sam quickly writes out an NQ algorithm but fails to evaluate its efficiency or totally forgets to check if the queue is already full before adding an item, the marks just vanish. Poof. Gone. Simply memorizing the definition of a FIFO structure is nowhere near enough at this level. You have to deeply understand what the examiners are actually digging for beneath the surface.
To build that perfect, unbreakable skeletal framework for your exam answers, we're going to dig systematically through 5 specific layers today. We'll start with core theoretical principles, move into technical methodology, unlock the method mark strategy, highlight those crucial examiner warnings, and finally, master algorithm evaluation. Let's get right into it.
Okay, layer number 1, section 1, core theoretical principles.
Listen, understanding cues isn't just about rote memorization. It's about building a robust theoretical architecture in your mind. You absolutely need precise definitions. You need to know exactly what a front pointer and a rear pointer do and how they behave dynamically. You need to grasp causal relationships, understanding that, hey, incrementing a rear pointer without a boundary check doesn't just look bad, it causes a catastrophic buffer overflow in a real system. And most importantly, you need integration with other syllabus areas. Whether you've built your foundations in 0417, 0478, 0983, 0984, or 2210, the destination is mastering this 9618 A-level standard where everything connects. This is exactly where I need to introduce you to the ultimate tool for this architecture. It's the PEEL framework: point, evidence, explanation, link. Top-tier students use PEEL to structure every single one of their computer science long-form answers. Your point is clearly identifying the Q structure. Your evidence is the specific algorithmic mechanism, like the exact math of how the pointers move. Your explanation is why this matters to the system's overall efficiency. And your link? That's tying it back directly to the context of the exam question, maybe linking it to memory management or processor scheduling. This is how you demonstrate that connected, deep conceptual understanding that transfers seamlessly to completely unfamiliar exam contexts.
The assessment objectives for QADTs heavily target these 3 distinct cognitive domains, and hitting all 3 is how you get awarded the absolute highest marks. Let's do a quick mental interactive spot check right now. If I read an exam answer that simply says, a Q is a first-in, first-out data structure, which domain is that? Well, it's just basic knowledge, it's surface level. But if the answer says, we implement a circular queue in this specific scenario to prevent memory wastage when the front pointer advances, thereby optimizing the limited RAM, boom, that hits application and analysis right on the head. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving deeper into our dig, section 2, technical methodology. Now, this 5-step procedural framework you're looking at is directly sourced from the exam methodology requirements. It's time for the transformation phase of our explainer. Let's look at exactly how we turn Sam's rushed, red pen-heavy answer into a field of green checkmarks by rewriting it live in our heads using these steps. I'm putting a mental 60-second timer on the clock for this rewrite attempt. Ready? Step 1. Deconstruct the command word. Sam saw evaluate, but he treated it like describe. Huge mistake. Step 2. Extract relevant data. The question specifically asked about a 100-element array queue, which Sam totally ignored in his pseudocode. Step 3. Select the framework. We're going to apply that Peel framework we just talked about. Step 4. Execute with clear notation. Instead of throwing out generic pseudocode, we write explicit, precise pointer checks. Step 5. Present with terminology. We don't say the queue gets full. We use professional words like underflow, overflow, and circular implementation. When you follow this exact blueprint, you are basically handing the examiner exactly what they want to see, structured in the exact way they have been trained to grade it. It's a cheat code.
So the absolutely crucial point here is that algorithmic thinking is a highly structured, logical sequence. It is not just a guessing game where you throw code at a page and hope it sticks. This is your computer science success blueprint. It requires step-by-step decomposition of the problem. It requires choosing the right data structure. I mean, ask yourself, is a linked list implementation of a queue better than a static 1D array for a system that needs highly dynamic data storage? Yes, absolutely. You need to know why, and you need to prove it through rigorous testing and trace tables. Let's move to Section 3, the method mark strategy. Stop scrolling. Subscribe to our YouTube channel AC Exams at acedexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acedexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Okay, we are back, and we need to talk about risk. There is a massive, fundamental difference in strategy here that separates the A stars from the Bs. High risk is providing the final answer only. High reward is showing your full, unedited working process. Let's dive into an interactive workshop right now. Challenge 1. Data scan. I want you to imagine a complex computer science data table showing state changes in a queue's front and rear pointers over 10 distinct clock cycles. The timer is ticking down. You have 60 seconds to extract the core trend. Many students, just like Sam, will frantically trace it in their heads and only write down the final state of the queue in cycle 10. Let me tell you, that is a massive, massive trap. Examiners explicitly state that method marks are awarded for showing the algorithmic process. If you make a tiny, silly arithmetic error on cycle 9, but you physically showed your step-by-step logic on the paper, your trace table, your pointer movements, your explicit boundary checks, you will secure the vast majority of the method marks. Writing just a final answer means one small mistake costs you 100% of the points. Always, always, always show your algorithmic working. It is your ultimate safety net.
Let's unearth Section 4, Crucial Examiner Warnings.
Avoiding these top 3 specific errors is literally the easiest way to jump a full grade boundary. First, answers are too vague. Saying something like, data goes in the back and comes out the front is completely useless at the A-level standard. Examiners want deep technical details. They want to read, the item is enqueued at the rear pointer index and the rear pointer is subsequently incremented. Second flaw, forgetting boundary conditions. This is time for challenge 2, find the flaw. I'm going to give you a flawed sample paragraph, and you have to spot the issue. Ready? To add to the queue, take the data, put it at the rear pointer, and add 1 to the rear pointer. Did you catch the flaw? There is absolutely zero check to see if the queue is already full before adding the data. You completely missed the overflow boundary condition edge case. That costs you huge marks. Third flaw, ignoring the specific context. If the exam question is specifically about a network router managing data packets, talk about data packets. Don't talk about abstract numbers or grocery store lines. Context is king.
The difference between an average response and a top-tier paper almost always comes down to context and technical depth. Let's do challenge 3, speed writing. You've got 30 seconds mentally to evaluate why a circular queue is better than a linear array queue for a continuous data stream. Go.
The difference between an average response and a top-tier paper almost always comes down to context and technical depth. Let's do challenge 3, speed writing. You've got 30 seconds mentally to evaluate why a circular queue is better than a linear array queue for a continuous data stream. Go. The difference between an average response and a top-tier paper almost always comes down to context and technical depth. Let's do challenge 3, speed writing. You've got 30 seconds mentally to evaluate why a circular queue is better than a linear array queue for a continuous data stream. Go.
And finally, the deepest layer of our dig. Section 5, algorithm evaluation. There is a very specific examiner mandate when it comes to algorithm evaluation, and you need to pay close attention here. When you are hit with an evaluate or compare command word, say comparing an array implementation of a queue versus a linked list implementation, listing similarities only will forcefully cap your grade. You hit a ceiling. The examiner strictly requires you to identify similarities and differences, and you have to use proper comparative connectives and hard evidence to do it. You must train yourself to use phrases like whereas, in contrast to, and conversely. For example, a perfect sentence looks like, both implementations successfully maintain a strict FIFO structure. However, whereas the array implementation has a fixed static memory footprint leading to potential space inefficiency, the linked list implementation dynamically allocates memory, which optimizes space but carries a slight performance overhead for storing pointer addresses. That is the exact level of critical comparative analysis that locks in perfect marks every single time.
To accurately evaluate algorithm performance quality and draw actual evidence-based conclusions, you must systematically detail these specific metrics. Time complexity. You need to state confidently if an operation is big O of 1, meaning constant time like a standard in Q, or if it requires traversing data, which changes things. Space complexity. Is it fixed or dynamic? Edge cases. What happens when it's empty? What happens when it's full? And finally, the effect on overall system performance. This entire breakdown brings us to the complete, definitive computer science answering system. If you want a cheat sheet, here are the 3 golden rules that guarantee top marks on QADT questions. Rule 1. Command word decoding. Never, ever describe when asked to evaluate. Rule 2. Peel framework application. Point, evidence, explanation, link for every single long-form paragraph. Rule 3. Time management matrix. Allocate your exam minutes directly proportional to the marks available, and always leave time to manually trace your algorithms to catch those edge cases.
So as we wrap up this massive excavation of the syllabus, I want to leave you with one final, deeply provocative question. Are you actively checking edge cases and evaluating time complexity on every single QADT practice question you answer right now? If the answer is no, you are leaving precious, grade-deciding marks buried in the dirt. Start applying this paleontologist strategy to your very next practice exam. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder: subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep digging, keep learning, and I'll see you in the next strategy session.